Very much. This is a very exclusive location and audience. Thank you very much for coming along after lunch. I feel like we should all have a drink in our hands or something in a saloon. So I'm a technology evangelist. That sort of is a bit of an odd title. It means I get to learn about interesting new open source technologies, try them out myself, build things, blog about them, and occasionally get to give a talk on them. So I'm really quite pleased that I can give a talk on this topic. And this is one of the first ones I did when I started with Instacluster about, it was last year when I did this project. So it's a bit out of date, which I apologize for in advance. So there's a few gaps, and there could be a few improvements as well. So there's some future work possible for it, but I'm basically just talking about what I did last year. It's not sort of on the edge in terms of IoT technology. It's more to do with core infrastructure. So hopefully that's okay for people that are more interested in edge technologies. It's not a real project, it's just a demo project. So it's realistic, but not correct or complete or all those other good things that you'd need to do in production. But hopefully it gives people some ideas. And it's the way I actually learned Kafka. So in a sense, you're going to hear about some of my mistakes and some of my sort of conclusions about how to actually get things working. So let's go. So what we'll see on our journey upriver is a bit of an intro to Kafka. Just can I get a show of hands to see who knows about Kafka? Who's used Kafka? Okay, so it's going to be a pretty basic intro. And then I'm going to look at the Kongo problem, which is a problem of my own invention. Next, I'll have a bit of look at the application, the architecture, and the possible designs for the system. Then I'll look at a streams extension that I did, and then have a look at the problem of scalability for the whole system. So that's what I'm going to talk about. Hopefully that's interesting to most people. So first of all, the Kafka introduction. So I work for Instacluster. We have a managed platform for a variety of technologies. We do multi-cloud, scale, performance, availability, integration, and security. So essentially we provide some of the missing pieces for some of the Apache big data projects in terms of the operations space. And also we look after the clusters for people so that customers don't have to worry about doing that themselves. So we've got open source technologies for storage, that's Cassandra, analysis, that's Spark, search, coming up this year is Elasticsearch, exploration, Kibana, and last year we added some streams technology, i.e. Kafka. So that was why it was an appropriate technology for me to start learning and start blogging about as well. So Kafka is a distributed streams processing system which enables distributed producers to send messages to distributed consumers via a Kafka cluster. So at that level, it's pretty simple, isn't it? It doesn't actually do anything itself. It's just a way of delivering messages to where you want them to go. Some of the benefits are that it's fast, it's got high throughput and low latency, it's scalable, horizontally scalable. You can just add nodes and partitions to increase the concurrency and the throughput. It's reliable, which is important for production environments. It's distributed and fault tolerant. It enables you to have zero data loss. It's open source, it's an Apache project. Quite a critical aspect is it enables you to have heterogeneous data sources and syncs. So it actually came from LinkedIn originally, and their problem was actually how they could re-architect all of their weird applications that were talking to each other point to point and remove the burden on integration of new applications. So they decided to use it as a hub-spoke sort of an architecture. And that's sort of where it came from. And it's still actually quite useful for that purpose as well, particularly in the IoT space. You're highly likely to have heterogeneous sources of data. So that's a great way of combining them all together in one system. And it's available as an Instacluster managed service, if that's the way you'd like to run it. How does Kafka work? Well, I've actually, a few months ago, I developed a visual introduction to Kafka. This is not that, but you can look at it on our website and download it later. This is the first sort of the few slides that are relevant from that. Let's have a look. So Kafka is pub-sub, it's publish-subscribe, it's loosely coupled. Producers and consumers don't know about each other. Filtering, or which consumers get which messages, is topic-based. Producers send messages to topics. Consumers subscribe to topics of interest. For example, in this case, there's a bit of a story around parties versus work. When they poll, they only receive messages sent to those topics. None of the consumers in this example will receive messages sent to the work topic, only messages sent to the parties topic. So there's two aspects about Kafka that I just want to focus on. First of all, it works a bit like an Amish barn raising. So this is how you get the shared concurrency aspect. Partitions and a consumer group share work across multiple consumers. The more partitions a topic has, the more consumers it supports, and therefore the more work can get done. On the other hand, Kafka also works a bit like the clone army. It supports delivery of the same message to multiple consumers with consumer groups. So because Kafka doesn't throw messages away like traditional messaging systems, immediately they are delivered, the same message can be easily delivered to multiple consumer groups. So this gives you the broadcasting capability. So just to see how that works in practice, consumers subscribe to the parties topic are allocated partitions. When they poll, they will only get messages from their allocated partitions. So this divides the problem down into a smaller scale. This enables consumers in the same group to share the work around. Each consumer gets only a subset of the available messages. On the other hand, multiple groups enable the message broadcasting. Messages are duplicated across groups as each consumer group receives a copy of each message. And in theory, you can have as many consumer groups as you like in order to satisfy the particular business case you've got. However, we'll see maybe there are some complications doing that later on. So the particular application problem that I came up with, I've called the Kongo problem. The reason for the name is that the Amazon was taken, obviously, Amazon and AWS, and Kongo is the second biggest river at 5,000 kilometers long, and it turns out to be the deepest river. So it is actually up there in a sense of being one of the most important river systems in the world. And why the odd naming? Well, it turns out that it used to be called the Congo with a K, named after the Kingdom of Congo that was at on the coast of the river. So hence the name. In terms of the actual application domain, it was very important and still is for trade. It's the main source of movement into Central Africa. And I was interested in developing an example logistics problem, so it seemed like a good name. So a bit more about the particular logistics problem that I had in mind. I had in mind the idea that there'd be lots of goods for a start, and the goods are going to be stored in warehouses, and the goods are going to be moved around between warehouses in trucks, or some other way of moving them around if you prefer. And I wanted to be able to also check lots of interesting rules in real time. So that's sort of the context. In a real case where would actually be all these things happening in the real world, there'd be an interface through sensors and RFID devices into the virtual world where all the software is running. For this particular demo system, the whole system actually is running in the virtual world, so there's no actual real component, but that's what the story would look like. So let's have a look at some goods. Here's some examples of goods. Chickens, they're perishable, fragile, and maybe even edible. We've got toxic waste. Well, that's hazardous and potentially bulky. We've got vegetables, they're perishable and edible. And then maybe we've got something like art, which is fragile and I guess potentially valuable as well. Warehouses, well, okay, you can just imagine warehouses. They're just places where the goods are stored before and after they're being moved around by trucks. Trucks, well, okay, they're the things that move the goods around between the warehouses. Right, and as I mentioned, there's an assumed interface between the virtual world and the real world. So we're assuming that all the goods have RFID tags on them. So you can identify what the goods are from their RFID tag. And when they go in and out of warehouses and trucks, you can detect when they're coming in and out. So we were also assuming RFID readers essentially at the boundaries between the warehouse system and the truck system, if you like. So the RFID readers produce load and unload events, basically. So every time a good is removed from a warehouse and loaded into a truck, we'll get a load, the goods ID, and then the truck ID. And every time they're unloaded, we'll get an unload event saying it's more or less the same in reverse order. Okay, so there's a slightly different part of the story is that we're assuming there's a whole bunch of sensors in both the warehouses and the trucks as well. So these are assumed to produce a whole variety of relevant metrics. For example, on the trucks, we'll have some sensors producing shock and vibration information. In the warehouses, maybe we'll have some environmental sensors, including things like temperature and gas levels and things like that. So the system assumes that there's about 20 metrics in total. Some are common across trucks and warehouses, some are unique for trucks, and some are unique for warehouses. So the story essentially works like this. So we've got, well, in this case, we've got two warehouses. It's about the simplest possible case, I guess. So there are some goods initially stored in one warehouse. There are no goods in the other one to start with. Each warehouse produces some sensor events telling us what's going on in that warehouse over a particular period of time. And what we want to do is check the rules for the goods to see if there's been any environmental violations for those goods in the particular warehouse that they are in. So in this case, you get all the sensor events from a warehouse for a particular unit of time. For every goods in that warehouse, you want to see if there's been any violations. There are no goods in the bottom warehouse, so there's no checking required. Along comes a truck. It arrives at the top warehouse, and we're going to load something on. Let's load some art on the truck. This produces a load event, and the system now knows that the art is in the truck, not in the warehouse. Let's load something else on the truck. Let's load some toxic waste onto the truck as well. May not be a good idea, but it happened. So we get another load event. We know that the drums are now in the truck, not the warehouse. And at this point, because there are two goods in the truck, we can run some checks on whether those two goods are actually happy to be together in the same small location, i.e. in a truck. We don't run these checks in the warehouses. We assume the warehouses are big enough that the different goods types can be segregated safely. But every time there's more than one goods in a truck, we want to check if there's any potential co-location issues. The truck then drives to another warehouse. While it's doing that, we assume that the truck sensor events occur, and we want to check to see whether all the goods in the truck are still happy with the environment that they're in terms of vibrations and acceleration and temperature and anything else that they may care about. Once the truck arrives at the second warehouse, the goods are unloaded, so we unload the drums and the art. All the goods are always unloaded when the truck arrives at each warehouse. This produces the RFID unload events, and the system then knows that the goods are in the warehouse. And then basically we just repeat in a loop, doing exactly the same thing forever and ever until we decide to stop it. Except the main difference is there's lots more warehouses, goods and trucks potentially. So I've already mentioned that there's a couple of different sorts of rules. So we've got rules for the categories for the goods. Each goods has 0 or more general categories for things like whether they're perishable, hazardous, fragile, edible, medicinal, bulky and dry. In the real world, it's a lot more complicated, of course. I got the idea for this from the Australian transport regulations for goods, and definitely there's 97 categories with a very, very complicated matrix explaining which things are allowed to be transported together. So there's also 0 or 1 temperature category for each goods, so going right from frozen through to anything that'll cope with just being at the ambient temperature, which in Australia can get pretty hot, so 40, 50 degrees potentially. And some warehouses and trucks are temperature controlled, so they actually ensure that the temperature is in one of these categories, one or more of these categories actually. Others aren't and can randomly go to any temperature. So how do the rules get checked? Oh, so first of all, this is an example, the collocation rules. So each good has rules to check if they are safe in the same truck as another goods category. So for example, you don't want explosive goods to be in the presence of spontaneously combustible goods because something really bad might happen. The sensor rules, on the other hand, work like this. The goods have rules to check if they are safe in the environment of a particular location, either the warehouse or the truck. And yeah, as I've mentioned, there's about 20 metrics, some in common. So you want to keep your chickens cool while they're being transported and if they're being stored in a warehouse as well, just as an example. So what does the application actually look like? Well, it's a simulation. The first step is that we create a whole system with a certain number of goods, warehouses and trucks, and there's a whole bunch of parameters that you can fiddle with at that point to create different numbers of categories of each thing and such like. And then there's basically a loop which gets repeated. The time unit is an hour in the simulation, so everything happens in hour boundaries. First of all, we simulate the sensor values for the trucks and warehouses. Then we check the goods and collocation violation rules to check that the goods are allowed together on the trucks. We unload the goods into warehouses. We check the goods and sensor violation rules for the goods in the trucks and the warehouses. And then we load the trucks with goods, move trucks to a random warehouse and repeat. So they're the logical steps. They're not necessarily exactly the ones we do in order, as it turns out. So initially I built the application as a monolithic architecture. You'll see the same steps there. Basically, the steps on the left-hand side there are the system which has perfect knowledge, producing some events, and the events are purely passed internally in the initial monolithic application to the checking rules in the two orange boxes there, which then produce some violations. Well, that's great. I mean, it works fine. It's just, it's not scalable and doesn't really demonstrate anything terribly interesting. So what we had to do is decouple the simulation side from the checking side using event streams. So as you'll see, there's a whole bunch of sensor events and then the RFID events for unload and load being passed from the simulation stack into the checking system on the right-hand side there. Okay, so the next step is to move to a real distributed architecture. So this is where we actually introduce separate Kafka producers and consumers. The producers are basically the application running the simulation on the left-hand side. The consumers are essentially the rule checking for the goods themselves. The simulation has perfect knowledge, but I did assume that the rule checking system relies on the event stream data for its context in order to make decisions about whether some of the rules are being violated or not. So I had some design goals. The primary one was that we wanted to deliver events produced from each location to goods in the same location. So if we have some warehouses and trucks on the left-hand side here, and the goods on the right-hand side are actually in those locations, and we want the sensor events and the RFID events in those locations to only be delivered to those goods, and always get delivered to those goods if you like. So there's at least two aspects to that. You want guaranteed delivery, and you don't want the event sent to the wrong goods at all. Now, in terms of how you would implement this in Kafka, well, because I was learning Kafka at the time, it seemed to me that there were a number of different variables, and therefore that impacted the design decisions that I could make. The first thing in Kafka that's important is the topics. So the topics are the mechanism that Kafka uses for delivering events to a destination. So it seemed relevant in this case. So there's two extreme possibilities, if you like. One is only having one topic. So in my case, I could put all the locations together in one topic. Or the other approach, which at the time seemed sensible, was to have many topics. And you could have one topic per location. In other words, one topic per warehouse and per truck. So that seemed like a clever idea. In terms of the consumers as well, some of the design choices I thought of at the time were where you could decouple the goods from the actual Kafka consumers. That seemed a bit complicated and unnecessary. So I ended up trying the one on the right bottom there, which is every good is actually a consumer, or a consumer group, in fact. So this meant that the number of Kafka consumer groups was actually equal to the number of goods in my simulation. Is that going to work? We'll see. So some of the problems with those two choices in particular. First of all, looking at the topic one, well, hundreds of locations or even potentially thousands means you have hundreds or thousands of Kafka topics, which is, I mean, you can sort of get away with a few hundred, thousands, tens, thousands, hundreds of thousands. Probably not so good for scalability for Kafka. And the other problem is if you have a very large number of consumer groups, you also have scalability problems, unfortunately, at that point. So the sort of the obvious way of doing this in terms of the design that fitted the data model that I had actually didn't turn out so well. So, yep, I'm going to have a look at the two extreme cases now and see how well they work. So the possible design number one, this is the one where you have multiple topics and as many consumers as there are goods, so lots of consumer groups. So it looks like an elegant solution. It sort of fits the data model reasonably well. Design number two seems a bit unnecessarily simplistic at one level. This is where you only have a single topic for all the location data and a single consumer group. And the goods objects in the system are essentially then decoupled from the consumers by another magic component that I will gloss over at this talk, but there is another component that I had to insert at that point which made a decision about which events were going to which goods based on location data. Yep. Okay, so I decided to check the design before I tried scaling the system out, just to see which of those two extremes actually worked well. So in a sense, the problem is related to the fan-out problem in Kafka. So how well does Kafka work for broadcast delivery of the same event to a very large number of consumers, which is actually a perfectly valid use case for Kafka. So don't be scared of that. Just don't do anything quite as extreme as what I was doing without thinking about it. So my initial benchmarking just on a small Kafka cluster with 100 locations, 100,000 goods, so a fan out of 1 to 1,000. So each event had to be delivered to 1,000 consumers. And you'll see the result here in terms of relative throughput. The first design is very, very poor in terms of throughput, and I was getting the maximum throughput for the system with the second design, which has the single topic and the single consumer group. So there's a massive difference in throughput between the two designs, which took me some time to work out what was going wrong and why I'd made those choices and how to fix them. So just a slightly different aspect of Kafka now. So I've talked about, that was a bit about really, in a sense, the Kafka consumers and topics. Well, there's another API in Kafka called the Streams API. This is actually really powerful and quite a clever part of the Kafka technology stack. There's another API as well which enables you to connect Kafka to other things as well, but I'm not going to talk about that today. And it turns out the Congo River actually has this crazy way of fishing. They basically just stick the nets in the rapids and wait for the fish to come along. So in a sense, Kafka Streams is a bit like that, maybe. It is highly scalable, the Kafka Streams mechanism, and again, the fishing does appear to be scalable in the Congo River there. So you can scale out your Streams application with things called tasks. Again, it's a bit complicated, but possible. So just as a bit of an overview, so the Streams API allows an application to act as a Streams processor, so it can consume an input stream from one or more topics and produces an output stream, again, to one or more topics. And it transforms the input streams to the output streams. So it's all about transformation. The stream is an unbounded, ordered, replayable, continuously updating data set consisting of strongly typed key value records. Yep. So streams have a topology. So a stream application is essentially a directed acyclic graph of stream processors called nodes that are connected by streams or edges. And they transform the data by receiving one input record, applying an operation to it, and then producing output records. There's a DSL for it. There is another mechanism which is a bit lower level again, but I only had a look at the DSL. So the Streams DSL has built-in abstractions for streams and tables. So there's a whole bunch of sort of weirdly named things to do with streams and tables there. And it supports a declarative functional programming style, which is, if you're familiar with that style, it makes it relatively easy to write a streams application. If you're not, then it's a bit harder to get your head around that. There's two sorts of transformations. There's stateless, for example, a map and a filter operation, as well as stateful transformations such as aggregations, including count, reduce, joins, and windowing. So it's got some quite complex stateful operations. One of the problems that I, as a beginner for the Streams API, had was knowing how to compose these operations together to actually produce something that worked and that did something useful. And it turned out this diagram is the absolute key to that. So this tells you, it's essentially a state machine which tells you which operations work together, what output is produced by each operation type, and what you can then do with the thing that's produced from that. So this is a pretty useful diagram. So the particular application extension that I decided to try out was checking if trucks were overloaded. It seemed like a natural fit to the logistics problem I had in mind. My simulation initially had no concept about how many things could fit on a truck, so I decided to impose some maximum load limits and produce the goods with known weights as well. And then I built a Streams application which could check for overloading for the trucks. So I won't show you the application. It's sort of complicated and nasty. It's on GitHub if you want to have a look. But some of the things that I discovered building the Streams application included getting lots of topology exceptions and floating trucks. What are they? Well, so it turns out that, well, so this actually is my Streams application. As you see, the topology is sort of a bit complicated. One thing I discovered that was really helpful for debugging it and also for finding out what was wrong with some of the topology errors I was getting is this thing, which is a third-party tool which gives you a visualization of the stream. So the first problem it solved was invalid topologies. I was getting topology errors. I had no idea what they meant, but yeah, being able to actually visualize using this tool was quite handy to work out that it actually made a mistake in this case, and I was using the same node as a source for two operations, which is not allowed. And my negative truck weight problem, well, had I invented antigravity or not? No, it turns out that there's quite a lot of Kafka settings that you have to think about and not just leave at the default setting, and that was what was catching me out. So I had to turn on the exactly once transactional setting. So this allows a transactional producer allows an application to send messages to multiple partitions atomically. So this actually solved my problem. My weights no longer went negative. So the final part of the story is about the scalability of the whole application. So it turns out that the Kongo River actually has the biggest rapids in the world. So it was a good choice of river, I think, as sort of an example for this type of problem. So the Inga Rapids are astonishingly big, haven't they? So let's go scaling. Is scaling easy? Well, I tried initially, well, in fact, this is what I finally ended up with was 100 warehouses, 200 trucks, which gave me 300 locations, and 10,000 goods in the system. So in terms of the scalability of the Kafka cluster itself, I tried scaling up and multiple clusters to see which ones would help. So you'll see initially, so three nodes of 2 cores each, 6 nodes with 2 cores each. This third option, which was a 6x2 and a 3x2 configuration, and then finally the 3 nodes by 4 cores each. So it does scale and in different ways. These are only relatively small clusters as well. This was just for a demo application. In production, the sky is the limit in terms of how big you can scale it up. The ability to split the application and put different topics on different Kafka clusters is actually quite a useful trick. So you can actually scale the clusters independently. And a lot of big users of Kafka do this, including Netflix. So you don't have to stick with just the one Kafka cluster. Bigger instance sizes actually have a huge impact on performance, probably due to the different network speeds that AWS allocates to instance sizes. So the bigger the instance is, the lower the latency by a long way. Probably the faster network contributes to that. So we actually run, some of our bigger instances are 8-core instances backed by SSDs, so they're quite powerful instances for running Kafka on. In terms of the total resource usage, so I've just been talking about the Kafka clusters so far. The application itself was a significant consumer of AWS instances. So it turned out that the application itself used about twice as many cores as the Kafka cluster, so it's not an insignificant part of the system. In fact, it's the biggest single part of the system that's running the application. So in my most recent projects, I've been using Kubernetes for doing the automation of the application provisioning and scalability, and that would be equally applicable for this project, even though I didn't use it. But that turns out to be quite a useful technology for managing the application scalability for systems like this. So did I have any other problems? How are we going for time? We've got another few minutes? Yeah, okay. So, we did manage to scale the system successfully, but as usual, there were a few things we learnt along the way. So it was actually quite hard to achieve linear scalability, which is a bit odd because Kafka is scalable, but you've got to actually take into account a few other things that can happen. The first problem I noticed was as a result of hash collisions. So what actually happened was I was getting an exception saying I had too many open files, which seemed like an odd sort of an exception. And this turned out to be due to an increasing and eventually too many consumers. And looking further at the problem, it turned out that some consumers were timing out. Well, why do consumers time out? Well, it turns out that if a consumer doesn't receive any events in a particular time period, they actually time out and say, whoop, I'm going away, and my system automatically then spun up another consumer. So I had 300 locations, but stupidly only had 300 petitions. And only, it turned out eventually 200 unique values. So only 200 consumers out of the 300 were actually receiving any events, which meant that the rest timed out and gave me this problem. So essentially this is due to hashing collisions. If some petitions get greater than one of the location values, then others are going to get 0, which is not a good thing. So this is actually a well-known problem. So it's been around since 1962. So I should have known about it, and I just wasn't thinking. It's the key parking problem that Knuth first actually wrote about in his career. So in a Kafka context, you have to ensure that the number of keys is a lot greater than the number of partitions. At least 20 times bigger is my rule of thumb. And the number of petitions, of course, have to be greater than or equal to the number of consumers in a group. Otherwise, some of the consumers won't get any data. Okay, the second aspect of scalability is probably not one you'll come across. Because I was doing this sort of as an experimental system, I was ramping up the load really quickly, running it for a while, and then killing the whole system. Well, this caused a problem called rebalancing. So I was actually getting rebalancing storms. Rebalancing storms in Kafka result in some consumers not receiving events. So you get a big drop in throughput for the system, often for significant periods of time. So, and it was also producing a very slow startup time for new consumers up to, and more in some cases, than 20 seconds. So you need to ensure that your consumers are started and are polling the Kafka system before trying to add lots more consumers. So I was essentially trying to create all my consumers at once, and that's not a great idea. And you also want to try and keep the total number of consumers as low as practical, as it turns out. And this is the third point. So if you've got too many consumers, scalability suffers, and you might get sucked into like a whirlpool, isn't it? So in general, for Kafka, less is more in terms of consumers. So even though we used the design with the least consumers in theory, if Kafka consumers take too long to read events and process them, then you need more consumer threads and therefore more partitions, which impacts the Kafka cluster scalability. So the solution is to minimize the consumer response time. So you really only want to use Kafka consumers for reading events from the Kafka cluster. And if you have to do any processing, including writing to a database or something, or running complicated algorithms or anything, running complicated checks in this particular case, you should do that processing asynchronously in a separate thread pool at least, or some other scalable mechanism. So my number one Kafka rule really is Kafka is easy to scale as long as you have the smallest number of consumers possible. So that's about it in terms of the formal part of the talk. The code for both the Kongo application and the extension, the Streams extension, is on a Github page. I've got a whole bunch of blogs on other sort of related topics. The latest one was on anomaly detection using Kafka, Cassandra, and Kubernetes. That also includes some Prometheus and open tracing from the monitoring side, which people might find interesting. There's an extension to that work doing geospatial anomaly detection with things like the Lucene Cassandra plugin and geohashes and stuff like that. There's my visual introduction to Kafka, which is sort of a fun overview of Kafka if you want to have a look at that. And you can find out more about our managed platform and sign up for a free trial and test out anything you like as well. So that's all from me. Thank you very much.
Questions, anybody?
We go for time, 35.
Hey, great talk. So you mentioned that if we are doing any processing with the consumers, it should get either asynchronous or like put it inside another thread.
Yep.
But wasn't that the whole point of using Kafka in the first place? So that
yeah, that's what I thought.
because we are using a log, so that we can do this. Like we could push all this stuff into a log and then easily do it afterwards. But now if we do the same thing, like we're just using another log for the same purpose.
Yeah, I tend to agree that it's a bit of a tension. I mean, Kafka will scale, so sure, don't get me wrong, you can put everything in your Kafka consumers, but then you will have to increase the number of consumers inevitably, and your throughput will suffer, in which case you'll have to then get a bigger Kafka cluster. So, I mean, there is a solution, which is just to make the cluster bigger, basically. And there are some tuning settings that I haven't played around with yet, but part of the issue, I think, is some of the default settings are not quite optimal for larger throughputs. There is a bit of a trade-off, though. I think there's sort of the application design, which may mean that you want lots of consumers, either accidentally or on purpose. But then, yeah, at that point, you really do need to think about whether your Kafka cluster is going to be able to deliver or not.
Questions? Oh, well, thank you again.
Good. I've solved everyone's problems. Thank you. Great.
So, round of applause. Thank you.